we can play. So she just said in 3.5, which is this implicit differentiation. She said 67. Yikes! Okay, I didn't get there. Okay, hang on a minute. We'll build our way up to that one. All right, hang on. Let's try this one. Let's try. Here, let's just try this one. I found this one in the book. 25x squared, this happens to be number 22, plus 36y squared equals 300. This happens to be, what I say, 22 in 3.5. So here's the new thing, and I don't know, sometimes I repeat myself a lot. The new thing Friday was we moved into 3.5, and we could deal with these. See, I want to say we can deal with these new implicit relationships, right? Where the x's and y's kind of are all just mixed up in their equation. That's new. Prior to this, we were dealing with functions. Y was a function of x. So we always had y explicitly written as a function of x. Y equals a bunch of x's. Y equals a bunch of x's. That's all we dealt with in the beginning of chapter 3 and most of this course so far. But you start mixing up your x's and y's, you get circles and ellipses and hyperbolas. I mean, you get things maybe that aren't functions. And they're written implicitly. The relationship between x and y is called implicit. Because because one of them's not by itself. They're just together, just mixed up in the equation. And therefore, these are beautiful relationships. They're beautiful curves. They're beautiful things. They may not be functions. They may or may not be functions as far as passing the vertical line test. But we can do their derivative. And we learned how to do their derivative. It's pretty cool. It's pretty easy. We learned that you walk up here and you start doing derivatives. And when you're doing the derivative with respect to x. So when you do an x term, you just kind of do it the old normal way. But because you're doing the derivative with respect to x, when you do a y term, you have to sort of treat y as a function of x, and so you do the power rule, 72y, is that right? But then you multiply by the derivative of the y with respect to x. It's almost like a chain rule concept, but it's an implicit derivative. When you do a y term, at the end of the y term, you have to do the derivative of the y with respect to x, which is dy dx, or y prime, or dy dx. We kind of don't like to write y prime in this situation. I don't know. It could get lost next to the y. You could lose your little. I don't know. It's right. It's correct to write y prime. I could write y prime, but I'm just saying, little stray marks on your paper and so forth. The prime is easy to get lost. You're looking for that dy dx helps see it a little clearer. Hey, what's the derivative of the other side? 0. Good. So guess what? We just did a derivative. But where's the derivative? The derivative is dy dx. The slope of the tangent line is dy dx. And where the hell is it? It's right there. So what we usually do after we do an implicit derivative is we have to solve for dy dx. So move the 50x over. Yeah. Move the 50x over. Negative 50x, divide by the 72y. Negative 50x divided by 72y. That's my derivative. I can simplify it. Negative 25x over 36y. Yeah, that's pretty cool, man. That's the derivative. And notice, it's implicit, meaning it has x's and y's mixed together.
That's not what the directions ask.
Well,
they ask multiple parts, like part A, find two explicit functions by solving the equation for y in terms of x.
Oh, okay. All right, so I grabbed this number 22 just to do this implicit derivative.
Right.
One reason I like 22 is because it's a classic ellipse. I don't know if you know that, but it's a classic ellipse. What makes it a circle is if they had the same coefficient. If that was a 25 and that was a 25, then it's a circle. But with the 25 and the 36 like that, this is an ellipse. It's not in standard form of an ellipse. We could play with that if we wanted to. I don't really think I want to. What I found is his derivative, which is his slope at any point. So he's saying maybe I didn't really follow directions. That's possible. That's definitely possible. I don't read too well sometimes. It said find two explicit functions by solving the equation for y in terms of x. So this is not how you would do this, but they would like to illustrate that you could solve for y in terms of x. Now, I'm going to do this quickly, you guys. If I try to solve for y, I think I'm going to get 300 minus 25x squared. You following me?
Are you going to do that on a test or quiz? The directions that are in the book, are you going to ask us that?
I don't know. It's hard. Sometimes it's, yeah, well, I mean, I might tell you that. I just don't know at the moment. Right. But it's worth listening to and jotting down or whatever, thinking. We're just thinking math. That's almost all we ever do in this class, except for a little bit of chit-chat. But we just think and do math, and it's all worth it. What am I doing? I'm solving for y. You with me on this so far? Hello? Divide by 36. Take the square root of both sides. I just solved for y. And it's plus or minus the square root of this mess. I just solved for y. Move the stuff over, divide, solve for y. And so now, if I wanted to, I could do what's called an explicit derivative. I mean, this is the way this has always been presented to you. And if I wanted to do this derivative, I could call it y prime, or I could call it dy dx, whatever I wanted to call it. But here it goes. How do you do the derivative of a big crap with a square root on it? Don't you write it to the 1/2?
Right.
And then you bring the 1/2 down, so it's 1/2, all that crap to the negative 1/2. Right, you guys?
Right.
And then I need to do the derivative inside. I need to do the derivative inside. That kind of sucks. I would pass over, I would think of it as 300 over 36 and just go past that because that's 0. I would think of it as 25 over 36, and then I would do a power rule, bring the 2 down, negative 50 over 36x. That's me doing the derivative of the inside with a little bring the 2 down power rule there. And we're done. You know, there was one thing out in front of this that I lost track of. What was out in front of this thing? There was a plus or minus. And so technically that little plus or minus is still sitting out here. I guess I got to bring it along the whole time. So this is my derivative if I do it implicitly. I mean, I'm sorry. Whoa. This was implicitly. Sorry. This was the old-fashioned explicit way, which meant I had to solve for y first. What a pain in the ass. And then I had to take this derivative, which was also a pain. I want to show you something. The point is, it works. I want to cancel this 2 with that 50 over there. Yeah. I'm going to leave the plus or minus out here, but I'm going to cancel that 2. That's going to be negative 25x over 36. I'm dropping this. I'm dropping this down into the denominator. If it's dropped, see, it's to the negative 1/2. It's nasty, dude. But I'm dropping it down into the denominator, and it's going to be down here with this 36. And so then it's going to be this bunch of crap here. Oh my God.
It's okay, but that's why.
over 36 all to the 1/2.
But that's why. So you have negative 36.
So she keeps saying that's y. Hang on a second. That's my derivative. That's my derivative, and I did it explicitly. Yeah?
The 1/2, where did that come?
I canceled the 2 with the 50
Okay.
and made it 25.
Alright, I see that.
Yeah, cool. That was slick, but I did that.
That's why, so it looks like that.
So that's my explicit derivative. I already done this thing implicitly. Guess what? They're the same. And how do you tell they're the same?
That's why.
This is negative 25x over 36 times this y. Over here, what is y?
That right there.
That's y,
That's what that is.
which is
The denominator.
that with that. Isn't that y?
Yeah.
So this is negative 25x over 36y. Is that what this is?
Yeah.
Yeah. Okay, it is. So that was the book saying, do it implicitly, but do it explicitly and prove to yourself that they're the same. And I just sort of did that. Yes.
Just a couple steps back when you went from the first line to going down to the negative, multiplied by negative 50 over 36x.
Yeah.
Did you not use the quotient rule to get that?
No, I didn't.
So how did you get that, or what
I know.
happened?
I did that quick. You're right. What I'm doing is he's and I knew that was gonna bother you guys. What I did was the derivative of the inside. I did it as quick as I could. Is that the inside? That's the inside, right, you guys?
Right.
Let me just show you how I wrote it, how I was thinking. I was thinking of it as a 300 over 36 minus a 25 over 36. I was thinking like that. So now I did its derivative. What's the derivative of this?
0.
0. What's the derivative of this? 50 over 36x.
Do you get the same answer if you do the quotient rule, like keeping it all together?
Yeah, let's do a quotient rule. You ready? Let's do a quotient rule. Derivative of the top times the bottom minus right down the top. I'm going to go off screen here, but that's okay. What's the derivative of the bottom? Derivative of the bottom? 0. All over the bottom squared. But that's a 0. One of those 36's cancels with one of these 36's. I think when I simplify this, I get this. All we do. I love math. You're welcome. Yeah. So earlier she asked about this. Is this going to be on a test or something like that? And anyway, now after doing this, no. If I present this problem to you, please do it implicitly like this. This is how you should do this problem. They're making me prove that if you did it explicitly, it would be the same.
Now that you did part A, you pretty much answered part C and D.
I might have. Yeah, I already did D, and I kind of did C, and I did B. I didn't do any sketching, but I don't, yeah. Here, let's try another one. Here's one, 32. Y squared equals log x. Is this 32? Yeah. Oh, and then I'm at the point E1. Evaluate the derivative at the given point. So I am at a point. All right, you guys. You ready? I want to do a derivative. I want to do a derivative. This is pretty darn simple, but it is not explicit. It's this new thing. It is implicit. So how do you walk up to some implicit dude and take a derivative?
2y.
Good job. Good job. That's how you do it. I mean, that's how you do that side. And you need to understand that. I hope you understand that. We practiced a lot of that Friday. It's easy once you get the little hang of it. Anyway, now I go over to the other side and I take the derivative. Well, the derivative of ln x is sort of, we should have it memorized, but it hasn't. We haven't been bringing it up in class too much. But it's 1 over x. It was a rule, it was one of our rules that we kind of, it's 1 over x. Oh, what did you say? You said it, ln, right, no. The derivative of e to the x is himself. The derivative of log x is not himself. The derivative of log x is this, right? So anyway, we're done. Wait a minute. We're done. Hang on. We did the derivative. We did the differentiation. But if I want the derivative by itself, I want to get the derivative by itself, then maybe I should divide by 2. I should do a little algebra here. Solve for dy dx. And I divide by 2y, and I get this kind of cool looking derivative here. This is my derivative. And I did it implicitly. And this is the derivative in general at any point, x, y. If they give me a point, they probably want me to plug it in and give them a specific slope. Did they give me a point?
Yes.
Yes, they did. So I should plug this point in and give them a specific slope. So at this point, the slope is, well, if you plug in an e for x and a 1 for y, I guess you get that slope. That's your slope. Cool. I thought 31 looked good. That was in your homework. 35's in your homework. Look at 35. They call this a bifolium. This is kind of interesting. It's this wild, it's this crazy looking curve here. It looks like this. See this curve? It's kind of a cool looking curve. They call it a bifolium. It could be wings of an insect. Not wings of an angel, whatever it is. Look at its equation. Its equation is kind of nasty. X squared plus y squared, the quantity squared equals 4x squared y. Is that it? That is it. Wow. So that's the equation of this crazy thing called the bifolium. They say I'm at this point 1, 1. And what do they want me to do? Find the slope of the tangent line at the given point. Hey, do me a favor. Don't do any math. Just look at the picture. Tell me the slope of the tangent line at that point.
0.
You think so?
Oh.
Good. You might be right. You know, maybe, unless I'm a little off. But you're right. Maybe it's looks like it might be a horizontal tangent line at that point. Looks like it could be a horizontal tangent line, and its slope is
0.
0. Yeah, so visually you might already know the answer if you're trusting my picture. You with me? Visually you might know that the answer is 0. The slope at this point kind of looks like it could be 0. If that point's a little bit over here, then maybe I'm off. Maybe I'm wrong. So maybe we should do all the calculations. So how do we do the calculations? We need to do an implicit derivative. It's going to be awesome. Ready? Here we go. Here we go. 2 times this stuff to the first. I mean, that's a power rule, right? And then I got to do the derivative inside, and it's all multiplied here. The derivative of this inside stuff. Now, how do you do the derivative of an x squared? 2x. Okay, good. Well, how do you do the derivative of a y squared? 2y, and you tack on a dy dx. That's how you do it. That's what we learned Friday. The video was up. Dy dx, that's awesome. Now that's, wait, whoa. That's this left-hand side. Let's go over here to the right-hand side. I got to do this derivative implicitly. Anybody want to say a word?
Is that a product?
Good job. It's a product rule. I got to do a product rule. I got to do a product rule. I know it's a little funny. We have to treat the x times the y like they're two different functions, and I got to do a product rule. In this implicit situation, even an x, just an x times a y is a product rule. This is a 4x squared times a y. Okay, here we go then. I'm treating it like a product. Derivative of the first, 8x. Write down the y plus
4x squared.
Write down the 4x squared, thank you, sir. And take the derivative of the y. When you take the derivative of the y with respect to x, it's called dy dx. dy over dx, dy dx. Yes. This is so awesome. I have myself a big, nasty, implicit derivative. I mean, actually, where's my derivative? It's buried in here. And to tell you the truth, solving for it, like we've been doing, right? You have to solve for dy dx and get it by itself. Solving for it would really kind of suck on this problem. I mean, it's buried in there. It's kind of, I'd almost have to distribute this. Look at me, I'd have to distribute this, I think. Then I'd have to get my dy dx terms together, get everybody else on one side, then factor out the dy dx. I mean, I could do all that. And maybe I should do all that, except timeout. I am supposed to evaluate this at a point. And so when someone gives me a point, then I'm a pretty smart guy. I tend to say, wait a minute, why do I need to do all that algebra? Can't I just plug in that point now?
Yeah.
Again, you got two options. Solve for dy dx algebraically and then plug in the point. Or plug in the 1 and the 1 now and then solve for dy dx, and it'll be easier to solve for it because you'll have a bunch of numbers instead of variables. So that's what I'm doing. I'm plugging in the point 1, 1. I'm plugging in the point 1, 1. That's a 1 plus 1. That's a 2. That's a 2 plus 2 dy dx. You guys okay? I'm plugging in 1s and 1s. I'm plugging in a 1, 1, so that's an 8. I'm plugging in a 1, so that's a 4 dy dx. Okay, now I got to solve for dy dx. That's a 4. I think I'll distribute that 4 through there.
I have a question.
Yes, sir.
You put in a 1 inside the dy dx?
No, sir. I'm plugging in a 1 for this. I'm plugging in a 1 for x, and I'm plugging in a 1 for y, and I'm searching for dy dx. It'll be my slope. I'm not plugging in anything for dy dx, right? I'm plugging in a 1 for the x and a 1 for the y. Hey, that's a 4, you guys. If you distribute it, it's 8 plus 8 dy dx on that left-hand side, and over here I have 8 plus 4 dy dx. That's kind of funny. When you subtract your 8, that's gone. When you subtract your 4 dy dx, you get 4 dy dx on this side equals 0. You're going to divide by 4. Guess what dy dx is? 0.
Oh, 0.
Yeah.
Didn't we predict that? Remember we predicted that?
I went all the way.
Visually? Remember? Visually we predicted that. We thought it looked like it had a slope of 0. But then we did the math, and I'll be darned, it has a slope of 0. Right. At this point, it has a slope of 0. This was a hell of an implicit derivative. Implicit derivatives. Well, if you get to plug in a point, you can. You know, earlier today, she asked me for this 67. The one reason I didn't want to do it is because it was something I didn't even get to. I didn't go over that. But maybe I'll go over now. So in 3.5, there's another little funny concept. Look at this. Look at this. I'm making up my own problem here. All right, look at this. I want to do a derivative. Here, hang on a second. Let me just make it worse. All right, good. Wait, let's make it a little worse. No. Look, I want to do this derivative. You know, I'm a reasonable man. I don't like triple product rules in the numerator of a damn quotient rule. I mean, that's what I got here. Are you with me?
Right.
I got a hell of a quotient rule. The damn numerator is a triple product rule. And chain rules all over the place. I mean, this is the worst problem in the world. This is chain, quotient, product all mixed together. So this is a bad problem. All right, so here's the book taught me this thing. I forgot to teach it to you. You ready? I'll teach it to you now. They taught me this thing called logarithmic differentiation. What they say is, before you even do a derivative, take the log of both sides. Okay? So I'm taking the log of both sides. That's the natural log. I'm taking the natural log of this side, and then I've got the natural log of this side. By the way, do I have to write all that? Can I just go to this side? So I got the. You guys ain't allowed to do that. When you have your master's degree, you're allowed to do that. You're allowed to take those little shortcuts. You ain't allowed to do it yet. All right. So now, the point is, I want to do a derivative now, but wait a minute. I got the log. I got the log of this huge mess. And what their idea here is that you can use the properties of logarithms. I'm sorry. I'm going to move up here. This is the log of y on this side. On this side, I have the log of all this stuff. And maybe you recall something about the properties of logarithms. Like if you have the log of a division, you can write it as subtraction. When you have the log of a product, you can write those as the addition of two logs. When you have exponents on top of logarithms, you can move them down front.
Right.
So it's those three log properties back from pre-calculus. They're kind of rare, funny properties, but you can use them now to bust this all up. And by the way, I still ain't done a derivative yet, have I? I'm not doing a derivative. I'm using a log of both sides to bust this left-hand side up, this right-hand side all up. I got to bust it all up. So here I go. I would say I have the log of x squared plus the log of that thing plus the log of that thing, because that's what you can do with the product. That's a minus sign, sorry, thank you. And then minus the log in the denominator. You guys cool? That's busting it up using log properties. Oh boy, I'm not done. I'm going to continue to bust it up. I'm going to use, see what I just did was busted up the product and the quotient using log properties with my plus signs and minus signs, right? Now I do want to bring those powers down front. I want to bring this power down front. I want to bring this power down front. Now look, what's funny about this is you're bringing a power down front. That sort of feels like doing a derivative, doesn't it? Yeah. But you ain't doing a derivative, right? You're doing log properties. Right. You're not doing a derivative, but you are bringing the power down front thanks to log properties. All right. Yeah, I mean, eventually we might do a derivative. Someday before this class is over. There we go. I brought all the powers down front. I used all three of my famous log properties. I busted up the product, I busted up the quotient, and I brought all the powers down front. Now, this is the easiest derivative in the world. Well, it's not the easiest, but it sure is easier than it was a few minutes ago. Now I'll do a derivative. Well, wait a minute. What's the derivative of this side? 1 over y dy dx. Good job. See, what I'm doing here is a little implicit derivative here. The derivative of natural log is 1 over y, and then because it's a y term, I had to do a little implicit derivative here, dy dx. I mean, it sort of became implicit when you took the log of both sides. It's kind of implicit now. All right, here we go. The derivative of this, 1 over x. That's the rule, 1 over x, with it multiplied by a 2. You could call that 2 over x, I guess. What's this? 1 over 3x plus 1? That's how you do it, right? But there's a 4 in front, so there's a 4 multiplied by that. And the chain rule says, after you do the log rule, 1 over 3x plus 1, you should do the little derivative of the 3x plus 1, which is 3. So that'll be a 12, if you don't mind. You guys with me? The 7 sits here. You do the derivative of the log. 1 over 5x minus 3 times 7. I mean, times 5. The chain rule times 5. And then the 1/2 sits out front, and I do the derivative of this thing, this log. The derivative of all the logs are 1 over whatever's inside the log. That's the derivative of a log. And then the chain rule says the derivative of the derivative of what was inside that log. Well, this derivative.
6x.
12x.
Oh yeah, 12x.
Good. 12x. Oh, yeah, 12x. Dude, the derivative's done. Where is it? We just did a derivative. It wasn't that hard. Remember, it was going to be horrible. We used the properties of logs to bust up what would have been a terrible product or quotient rule. The properties of logs busted that all up and made the derivative sort of easy. Sort of. Well, where's the derivative?
dy dx.
Oh yeah, the derivative is dy dx. Damn, so if I wanted dy dx, what do I have to do? Multiply by y, he just said. He's right. I got to multiply by y. So now y shows up on this side. Oh my God, what else is on this side? 2 over x. Well, all this stuff, right? 12. Can I do this? Wow, what a pain. Hey, I'm going to cancel the 1/2 with the 12x and call that a 6x. Is that okay with you?
Yeah.
Oh my goodness. I think we're done. Unless, who volunteers to get a common denominator?
No.
Come on. Come up to the board and get a damn common denominator for your classmates.
All those multiple.
I don't want to do it either. And you know what else they'll do? The final answer in the back of the book,
Yeah.
you know what they'll do? They probably will get a common denominator. Here's the other thing they'll do. They'll put y back in its place. What is y? See this y here? What was y? What is y?
That's about there.
Oh, there it is. So they'll grab this and they'll slide it right here in this spot for y.
Oh, shoot.
And then they'll have all this next to it. And then somebody might decide, well, let's get a common denominator. Anyway, 3 hours later, I don't know what you learned. You learned how to do algebra, I think.
Yeah.
Here, let's do a different one. Let's do a simpler one. Which one did she ask me about? 67? I'm sorry, I did a terrible one. See, 67 is pretty terrible. I don't really want to do that one. But now you got the point. You can do it. Let's do a simpler one. What about this guy? Yeah. See, no, but there, I'm sorry.
Okay, 67. Okay. I thought that was 66.
Nobody's ever taught you a rule for this. You don't have a rule for this. Never seen it before, I know. But if you want its derivative, you don't really have a rule for it. Because what do you have a rule for? You have a rule when you have x to a power that's not a variable. You know, when you have a number, you have x to a power, you got a rule for that. And you have a rule for when you have e to the x. Or, to tell you the truth, I never told you this rule, but you also have a rule for a to the x.
Yeah.
But I never taught you that one. But this is when you have a number raised to a power. This is when you have, a number raised to a variable. This is when you have a variable raised to a number. This is a variable raised to a variable. I'm saying I think you could do this logarithmic differentiation. It's not hard on this one. I think you should start by taking the log of both sides. We're trying to do a derivative, but I don't know how. So I'm going to take the log of both sides. So I'll have the log of y equals the log of x to the x. And what's the point of that?
To get that x down.
You can bring this x down. No, I don't want to cancel the log. I just put the logs on there.
Okay.
And I did it, the point of it was to get this x down. To use the log properties to manipulate this, yeah. Now, again, bringing that x down was not doing a derivative. That was just log properties. But I think you could do a derivative now. It would be a little implicit derivative. On this side, you call it 1 over y dy dx. And on the other side, it would be a product rule. Thank you. It would be a product rule.
So,
Derivative of the first, 1. Write down the second, plus,
1 over x
write down the x.
times 1 over x.
Take the derivative of log x.
1 over x.
1 over x.
Can't.
I'm going to call that the natural log of x plus 1. Is that okay with you guys? The plus 1 is not part of this argument, though. If you want the derivative, what do you have to do? Multiply by y. So right at the end, I'm going to put y right here. Now, what's y?
Y is x to the x.
There you go. It's x to the x multiplied by this. That's not that difficult. Here, you guys try this one. Try that one. Same thing. Do log properties. I'm going to hit pause.